Welcome to the WERA 103 presentation today. We're pleased to have you join us in this series of scientific discussions sponsored by the Western Regional Work Group. Today we're pleased to hear from Dr. Eric Bremer. Let me briefly introduce you to Eric. Eric grew up in British Columbia and then moved on to Saskatchewan, where he received his master's and PhD degrees. For the last 8 years or so, he's been heading up the research and development programs for Western Ag Innovations. And I think you'll find this discussion today on plant root simulators extremely interesting as they develop this new technology for estimating nutrient availability for crops. So Eric, with that brief introduction, let's go ahead and turn the presentation over to you, and you can go ahead and begin.
Great. Thanks, Rob, and thanks for everyone joining us. So, as Rob said, what I want to talk about today are plant root simulator probes. What are they? How do they work? And how we can use them to measure bioavailable nutrients in soil. So here's what they look like. They're basically ion exchange membranes in a plastic support, a stake that's easily inserted into soil. So about 6 inches long. And as you can see, there's two types here. There's the cation probe. The membrane here has sulfonate groups, which are negatively charged, that are fixed on a polystyrene matrix. And so it will attract and absorb cations, such as calcium, magnesium, potassium, and ammonium. And it attracts and absorbs these nutrients sort of like how a plant would absorb these nutrients. That's why we call them plant root simulator probes. It's not exactly like it, but it simulates what they're doing. And so they do that, and they also have quite a large capacity to hold these nutrients. So well, for the cation probe, the 37 milliequivalents per meter squared of membrane, so that would be equivalent to holding about 16.2 milligrams of potassium. The anion probes, they're orange, and they have an ammonium group, fixed group on the matrix that's positively charged. So that's positively charged membrane, and so it will attract and absorb anions such as nitrate, sulfate, and phosphate. And it has a capacity of 149 milliequivalents per meter squared, so that's enough to hold 3.6 milligrams of nitrate nitrogen per probe. When we're getting them ready to use, what we want to have is have these ion exchange surfaces completely saturated with something that is easily displaced when it's by other cations or anions in the soil. So for the cation probes, we have them completely saturated with the sodium ions. For the anion probes, we have carbonate ion saturated the probes. We also include some EDTA, which enhances, well, sort of simulates chelates and organic acids in the rhizosphere and increases the availability and ability to measure micronutrients such as iron and manganese and other metals. So quickly, how we work with them. So after you take them out of soil, you actually have to clean them thoroughly. And as long as you're using deionized water, whatever is absorbed on them will stay on there. You do a great job of cleaning it, because after that, you're going to we throw them into 0.5 molar HCl, and that will displace any of those ions that are on the membrane into the 0.5 molar HCl. And then we can take that liquid and we can bring it over to our analyzer, or nitrogen analyzer for nitrate and ammonium, or our ICP analyzer for phosphorus, potassium, sulfur, calcium, magnesium, and micronutrients. So a total of 13 different nutrients. So that's what they look like. What I want to next explain is what happens when you put them in soil. When you put them in soil, initially they will take up nutrients, other ions are absorbed relatively quickly, and this what I would call is the diffusion dependent stage. So it really depends on that concentration gradient between what's in soil solution and what's on the membrane, and then also the diffusivity of that soil, which is strongly affected by moisture. Over time, there will gradually become an equilibrium between what's on the membrane and what's in the soil. So over time, we'll eventually come to some kind of an equilibrium that depends on the relative activity of ions in soil with what's on the membrane. So just to show how that might work, the first example I show here is a 3-hour burial in a saturated paste of nitrate. So what we have is a short burial period, a saturated paste, so we have high diffusivity, and we have nitrate nitrogen, which is all is completely present in the soil solution. And what we can see is that our extractable soil nitrate nitrogen is really just exactly proportional to what is absorbed on the PRS probes. If we instead look at maybe something like potassium, we might see that the extractable K isn't as closely related to what we get absorbed on the probes. And of course, that makes sense because one, what's extractable is actually includes a lot of stuff that's on the exchange in soil. So it's not just what's in soil solution. The other factor that influences what gets absorbed on the probes is the other cations in the soil. And so we actually can show that if we account for calcium and magnesium in extractable, we can actually get a much closer relationship. So it just kind of shows that what's happening on the probes really does depend on what's going on in the soil. But again, these are just short-term wet things. What happens when we put these probes into real soils? And here's an example with 3 different soils. They're all at field capacity, and it's over 1 week. So we've got burial periods varying from 3 hours, 1 day, 3 days, and 7 days. What we can see is with nitrate, it continues to absorb nitrate almost linearly throughout that whole 7-day period, with large differences between soils. If, on the other hand, we look at phosphorus, the pattern is quite a bit different. It goes up quickly, and then it comes to a sort of equilibrium relatively quickly. You can kind of see again, there's a constant difference between these different soils. And potassium is more like, it's a little bit intermediate, but acts more like phosphorus. Comes up fairly quickly, usually is one of the quickest ones to come to some sort of equilibrium. But what about impact of something like moisture? So what I have in this here thing is 2 soils, a clay loam and a fine soil. And we have them either dry, moist field capacity, or saturated. And so of course, when you put a probe into PRS probe into dry soil, diffusivity is really low, and so the absorption of nitrate is much slower than if you put it into a moist soil. And you can see that in both soils. However, you put this into a saturated soil, sometimes it might go faster at first, but then you sort of run out of air, denitrification starts, and then plummets. And that's what we call a dynamic equilibrium. Not all soils are going to show this. It's probably a little better aeration than this fine sand, but still it's lower. If we look at another ion such as sulfate, also mobile, we see the pattern even more clearly. There's our dry soil, there's our moist soil, and then in this case, consistently, the highest rate of absorption and amount absorbed in the saturated soil. Similar, the same soils now, but looking at potassium. And again, we can kind of say, yes, at first, much slower in the dry soil, but in contrast to the mobile nutrients, it comes to an equilibrium at about the same level in all these different soils. We have different levels between these 2 soils, but by the end of the 7 days, almost independent of moisture, they come to what this soil can supply. Final example, manganese, which is essentially 0 in the dry soil. somewhat elevated in the moist soil, and really supply really increases when it's saturated. Probably the redox is going down, transforming that manganese to the more mobile, reduced form. What happens though if conditions change? So here's another experiment with one soil where we put the probes in dry soil for 7 days. And then we took that probe out and we either put it right back in or we put it into a saturated soil. At the same time, we also did that in a saturated soil, went for 1 week, and then either left it in the same or we put it in dry soil. And what you see that happens is that the probe in the dry soil, once it's put into saturated, very quickly comes up and looks like the saturated soil. But the probe that was in the saturated soil, even though once you put it in the dry soil, still keeps all its ions. And what's happening here is essentially that there's opportunity for exchange in that saturated soil. It's going to come right back up, whereas there isn't, once that probe, which is already full of, or it's already at sort of equilibrium with what's in the soil, you put it in a dry soil, there isn't that opportunity to displace those ions, and so we kind of stay up at the same level that it was. And if you look at potassium, this here soil actually has somewhat higher K in the dry soil than the saturated soils. That happens in some soils. But again, once you put it into a saturated condition, it resembles the saturated condition. When it's saturated, it just stays the same. Comes up to equilibrium quickly, stays there through the whole period. Final example, manganese, like you say, when it's dry, it's just very low. Once it goes saturated, it quickly comes up. And this is one of the few nutrients that actually almost measurably declines once it goes from the wet to the dry, but it still doesn't come exactly all the way. And that just shows that we're working, in this dynamic equilibrium sort of system. All right, these are all sort of lab things. Now let's go out to the field and have a look at what happens once PRS probes are installed in the field to monitor. Well, here's one of my favorite examples from Oregon. Stephen Salisbury and Neil Christensen did this study way back in 1998, and they looked at the nutrient dynamics following crimson clover versus following spring oats. And as you can even see from this picture, yeah, there definitely should be some big differences in at least nitrogen. But what they did is they, starting on the 22nd of October, they installed probes weekly for 8 weeks, so 8 one-week burials, and they compared that instead with 2 4-week burials, and they compared that with 1 8-week burial. So all in the same study. So here are the results. So on average, over those 8 weeks on the oat, we have 162 micrograms of nitrogen per 10 centimeters squared of membrane. If we had instead left them in for 4 weeks, yes, we got some more nitrate absorbed onto them, but not 4 times as much. It's actually about 1.5 times as much. We leave them in for 8 weeks, again, further absorption, but not 8 times. It's about 3 times as much. So you can see that from 4 to 8 weeks, we are almost doubling the amount of nitrate absorbed. When we put these same probes into clover, we get exactly the same pattern, but now we see that we got much more nitrogen following the clover. Whether we look at after using 1 week burials, it's 1.6 times higher in clover, or 4-week burials, very similar, 1.5 times higher, or 8-week burial, it's 1.3 times higher. So it's always higher, same direction, but we actually feel that we get a better relative measure if we go for maybe 1 to 4 weeks of burial rather than just leaving them for the whole 8 weeks. And that more closely resembles what happened with crop nitrogen uptake at 8 weeks, was 1.6 times higher following clover than after oat. Looking at this in a more fine grain like these weekly, you can see more things going on. And what you can actually see is that initially the clover was much higher than after the oats. But over time, two things happen. One is nitrogen supply decreased dramatically, and two, the differences between these two treatments also decreased dramatically. And what's happening is here is that November rains hit Oregon, and what we're certain to happen actually was all the nitrate got leached below the layer where the membranes are, and so therefore the differences and the amount of N supply declines. And that just really shows that it's almost more important is to make sure that you get the membrane, the probes placed when differences are there. So don't wait for all your nitrogen to disappear, or if you've got plants growing in there, wait for them to take up all that nitrogen, because what gets onto the probes depends on what's in soil solution or gets released to the soil. So we do the same thing looking at phosphorus. Again, see there's a bit of an increase from 1 week to 4 week, but only about 30% higher, or 8 weeks, again, a bit more of an increase, 1.4 times higher. But again, we get a consistent difference between those two treatments, on average about 80 to 90% lower following clover in this case than following the oat. And if we look at the pattern over time for those 8 weeks, what we see instead, in contrast, what we saw with nitrate is that these increased over time. And of course that makes sense because phosphorus doesn't leach out of the system, and actually higher moisture increases the phosphorus supply. So this is what you would sort of expect. Again, showing the importance of when you're actually using the probes to see what's going on. And I almost always say it's really, in dry system is okay to use them, but wait to see 1 or 2 precipitation events. And then you'll get a really much better understanding of what that soil impact is. Finally, example, same study, looking at potassium, and now we see really no difference on average absorption by the probes for 1 week, 4 week, or 8 week. Potassium quickly comes to an equilibrium, but the interesting thing is that the clover is consistently much higher than following oat. And that was, I think, a surprise. And one of the benefits of using something like a PRS probe is when you're looking at all the nutrients at once, you quite often find out that there's other things going on that you didn't expect. All right, that gives you some idea of when and where, or when and for how long you would put the probes in to figure out what's happening. But the next thing to think about is, well, where are you going to place them? Now, in most cases, the conventional method of using them is just to install them in that surface layer vertically. But you can kind of see that there's other options. Here we are right beside a river, putting them in the side, or you can put them horizontal at different depths, looking at what's happening. You can put them down an access tube if you're interested in following perhaps nitrate leaching, or you can put them in at an angle and look at just what's happening really close to the surface. Or you can put them in these, what we call these root exclusion cylinders, and look at what's released independent of roots. And finally, you can take soil samples and bring them to the lab, and under more standardized moisture and temperature conditions, have a look at what the impact is of different soils. Now here's an example of a study where I basically went out to a long-term no-till soil in early June, just to look at what the impact of depth. Now in this case, I actually took the top inch, the next inch, and then the next 2 inches, and the next 2 inches, and I brought these to the lab and did a 1-day test with them. And what you can see is that there was a lot more nitrate supply in that top inch than there was in the next, and almost none at depth. And that was because in this year, It's not going to always happen, but it was a drought year and it's a no-till situation, and this sort of thing can happen, and it just shows the importance of where, at what depth you would be. Well, if you're sampling soil, don't miss that top inch. Or if you're placing PRS probes, you want to put it in this zone where all the action is. Look at phosphorus. We got the highest activity in the next depth, and that's just because that's the depth where the phosphorus is banded. Potassium is more like the nitrogen, because most of the potassium cycling in the soil is from crop residues, which are coming in on the surface. My next example is actually from another study where, again, this one was in a lab, and we were looking at what's the impact of flooding of a control or non-manured soil versus a manured soil. And so we put the soil and then we flooded it. So this is actually underwater. And then we put the probes vertically, horizontally, but on its side, or we put them flat on the surface. And the idea is that maybe this oxidized surface layer should have very different nutrient dynamics than at depth. And in this study, we only put these probes in place for 3 hours, but we did it after 3 days and after 14 days. And here's the results for manganese. And you first notice the axis here is a logarithmic axis. And what we can see is that the probes placed flat on the surface are like 2 orders of magnitude less than if it's very deep. Or if we leave them for 14 days, we're another order of magnitude higher. So large differences between time and between where you are on the soil, on the surface versus inside. Our manured soil is also very high, but less differences among placement, and that's just because this soil really decomposes quickly becomes very anaerobic, and the whole soil became anaerobic. When we looked at another element such as phosphorus, we see, again, this is not on a logarithmic scale. We still see somewhat the same patterns happening, but now the big difference is between the soil. So this here soil is 2 orders of, is about 120 versus this soil, which was only about 1 or 2. So lots of stuff always happening where and when. Final example I wanted to talk about was what's the impact of plants growing and how one would maybe study this. And here's some probes, and it's an intercropping study, some canola on this side, some lentil on this side. And we just use this what we saw was that the canola was very effective at reducing the amount of nitrogen in the soil, so this guy had to fix more. It was all really cool. But what I wanted to maybe show in a bit better way is what's the impact of using these root exclusion cylinders. So this is a study by Quay et al., and it's in a poplar, I think, plantation. And what they did is they did a 2-week burial, either in the fall, just outside, and then in early spring in May, without and with the root exclusion cylinders, and in August for 2 weeks, in October. And as you would expect for nitrogen, during the period when there's a lot of nitrogen release and there's a lot of uptake, then there's a large difference between exclusion cylinders and non-exclusion cylinders. Whereas it really doesn't make much difference in the fall. We see more or less the same thing with ammonium, not always quite as extreme. Interestingly, we actually see the opposite pattern with phosphorus. And that's actually something that we often see. In other words, we see higher supply with roots in the presence of phosphorus. And that makes sense because really phosphorus is hard to get at, and plants do a lot of things to try to increase the availability of that, organic acids, releasing chelates. And so what we're seeing on the probes reflects what the plant is probably doing in the rhizosphere. Last one, potassium, not much difference between those two, whether they're in the cylinder or without them. And again, that makes sense based on how potassium works. Final example, we have Vern Barron looked at nitrogen supply over 24 weeks using 2-week burial perennials. And when you put these probes in with the roots in the old perennial stand, you get very low nitrogen supply. But if you put in root exclusion cylinders, you can see much higher values. And these values in the root exclusion cylinders are closer related to the relative ratio in nitrogen uptake. So 200 versus 140 kilos N per hectare uptake by the crop is closely reflected by what we are seeing without competition from roots. The PRS probes have actually been in use since 1994, about 25 years, and more than 400 papers have been published using them. And I just wanted to show here where they've been used. So it's about 38% of the research use has actually been in forestry, only 23% actually in agricultural systems. Grassland, another 17%, and then we have desert, polar, urban, wetland. So you can see many different environments that they can be used and are used. To give you some idea of what kind of range and supply rates you might see, here I'm showing for like more than 10,000 samples that are either agricultural, forest, or grassland, all from temperate ecosystems. What kind of measurements can you see? And you can see this here axis is base 2, so it goes 2, 4, 8, 16, 32, up to 1,000. So nitrate supplies range from basically 2 to 1,000 or more. And we can kind of see, yes, the ag systems tend to be definitely skew higher, forestry in the middle, and grasslands the lowest, the most competitive for nitrate. So nice differences, but you can also see that in each system. There's large range depending on soil and treatments and that sort of thing. So lots of wide variation among, but also within these different ecosystem types. Ammonium, on the other hand, was actually almost always as low and is quite similar between these different ecosystem types. And that just reflects the fact that ammonium is absorbed by soil and generally is very rarely high, except under maybe extreme conditions like fertilizer band or beneath a decomposing animal. We look at phosphorus, values range from about 0.2 up to maybe 100. And again, maybe just a little bit more